Welcome back. We are going to continue with power series and Taylor series problems and then move on to complex numbers in whatever time remains. So, without much further ado, last time I considered a general power series of the form an x minus a to the n. A is some particular constant, and the an's are the coefficients. And this doesn't have to start at 0. It could start anywhere. Doesn't really matter. Okay, so I want to remind you that for every x that you plug into this series, you get a regular old series. So the example one of the examples we looked at was the series x to the n of n factorial. This is a special case with a equals 0 and an is 1 over n factorial. If you apply those two rules and substitute in this general series, you get this particular series. And remember, for any value of x that you plug in, you get a different regular old series. And we're asking, for which values of x can you plug in and get a series that converges? In this case, the answer is all x. And so I was drawing a number line like this, and I was putting check marks where it converges. In this case, it converges everywhere. On the other hand, the geometric series, x to the n, and this corresponds to a equals 0, but an equals 1 for all n. We've decided this only converges between minus 1 and 1. It diverges outside, and also this particular one diverges at these endpoints here. So I'm taking special care to indicate that it diverges. So the general situation either looks like this or something like this, where you've got a center in general, and we did discuss this last week. This geometric series does not converge at the endpoints. It diverges at the endpoints. So I put these x's. Okay, so the question, for the point of the video, the question is, doesn't it converge at the endpoints? No, it doesn't. When x equals 1, you get the sum of 1 to the n, which is 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. If anything equals infinity, infinitely many copies of 1 added together equals infinity. So this diverges. Fails the nth term test, at the very least. But you can see that it's got to be infinite. So, same, at minus 1's a little different, because you end up with 1 plus minus 1 plus 1 plus minus 1. So the thing oscillates between 1 and 0, the partial sums, but that doesn't converge either. Anyway, the general situation is that you have some radius of convergence, which I'm calling capital R. As I said, I did do this last time, and the center is A, and what you're interested in is some number R where it converges in there, and it diverges out of there, and you have to check the endpoints separately. And I did some examples of this last time. I want to just do one more example, because I didn't do enough examples for my satisfaction. Anyway, maybe I'll even do 2. The point here is that this is the common situation, although it is possible to have an infinite radius of convergence where R would be infinity and you have no divergence at all, such as in the first example above there, the x to the n over n factorial. It's also possible to have a radius of convergence of 0, but it still converges at A. So it's always got to converge at A. But maybe it doesn't have to converge anywhere else. So let's look at an example of this last phenomenon. If you just consider the series n factorial x to the n. All right, so where does this converge? I'm not writing up the question, I really should, but the question for all of these is, for which values of x does this series converge? What is the radius of convergence? And for extra measure, is the convergence absolute or conditional? Right, so anyway, to deal with almost all of these problems, as I said last time, use the ratio test. Just treat it like a normal series, but with the ratio test, just don't forget that x is going to be a constant. You're going to plug in some value of x. And so the limit, everything is as n goes to infinity. So we consider the limit as n goes to infinity, and I'll call it capital A. We were using little a n. Problem is that maybe you think of this as little a n. I kind of want the whole darn thing to be called something, so I don't know what to call it. I'll call it capital A-N. Anyway, the point is that you've got to write down, don't forget the absolute values. They're absolutely vital here. Bit of a pun, whatever. Copy the term n factorial x to the n here, and then replace n by n plus 1. But not x. You've got to replace n by n plus 1 in parentheses. So that is the n plus 1th term of the power series over the nth term. Now, we've seen before that n plus 1 factorial over n factorial just reduces to n plus 1. I'm not going to do that again. As I say, we've seen it over the last few weeks. You just have to write out this in full from 1 up to n plus 1 and cancel out all the ones from 1 to n, all the products and factors, and so you end up with n plus 1. That's positive, so I'll pull it out. You get n plus 1 outside of, well, let's come back over here for 1 second. We'll cancel this out. X to the n plus 1 over x to the n is just x. So this becomes here the absolute value of x. All right, we have to take this limit, and it's vital that it's as n goes to infinity, not as x goes to infinity. X is being held constant here. So the question is, what happens to this when n goes to infinity? Well, there's two cases. If x is not 0, then this is some positive number, and then you multiply it by n plus 1, and it's going to get larger and larger. For example, if x is 2, this is just 2n plus 1, and of course, as n goes to infinity, so does n plus 1, so does 2 times n plus 1. And it doesn't matter if it's 2 or 3, any constant. So this is equal to infinity if x is not 0. But of course, if x is 0, then this whole expression is 0 for any particular n. And then when you take the limit, you'd be taking the limit of 0 in that case. So of course, this limit is 0 if x happens to be equal to 0 only. And what is important in the ratio test is whether that limit that you get is less than 1 or greater than 1. If it equals 1, you're in trouble. But in this case, 0 is certainly less than 1, whereas infinity is certainly bigger than 1. So in this case, it diverges, and in this case, it converges absolutely. It's not very exciting. Basically, this shows that the series here converges absolutely when x equals 0 and diverges when x is not 0. And so my picture, the center is 0. We have convergence at that one point. In fact, absolute convergence. And diverges everywhere else. The problem is that the n factorial is just too big. It grows much quicker than x to the n. And so the series never converges. Except when x equals 0, then of course the series is just 0 factorial, which is 1. So when you plug in x equals 0, you get 1 plus 0 plus 0 plus 0, which of course converges, as we've seen by the ratio test. Question? How come I'm not doing L'Hopital's rule here? Can anyone tell me why I didn't do L'Hopital's rule? I'll tell you if no one wants to tell me. But what's wrong with doing L'Hopital's rule? You need a ratio. It needs to be infinity over infinity, or 0 over 0. This is just some constant number times n. Would you use L'Hopital's rule to do this? Or 3n plus 1? If you did, you get the wrong answer. That limit is infinite, but the derivative of it is 3. So there's no L'Hopital's rule. Of course, if you express it as a ratio and you try to do L'Hopital's rule, which makes more sense, it still doesn't work, of course, but you get 3 over 0, which at least alerts you to the fact that you're doing something wrong. All right, so that's that problem. Let's do a couple of others. I did, as I say, already a couple of others, but all right. How about okay, maybe I'll just do one more. If you weren't here last time, or if you haven't watched the video last time, I suggest it's online already on the Blackboard site, or it will be on Calc Lifesaver pretty soon. You should look at the last 10 or 15 minutes of last time if you weren't here, because this is really a continuation of that. So this will be the final example of this type of problem. I propose to ask you the same question about this particular power series. Where does it converge? Is it absolute? Etc., etc. Now, in this case, as I said last time, that most of these problems you use the ratio test as I did in the previous problem. But this one is actually better to use the root test because you can easily take the nth root of everything around. Right? The factorials always use the ratio test. But here you've got an nth power, n squared power. Not a big deal. So let's apply the root test instead. So it's very similar to the ratio test, except that you start out with a different limit. You take the nth term and raise it to the 1 over n. So all I'm going to do is make sure you take the absolute value, copy the entire term from the series, 3 to the n over 2 to the n squared, x plus 2 to the n. We're going to take the absolute value of that and raise it to the 1 over n. So that's how you set up the root test. Very similar to the ratio test, as I said, but you don't take an plus 1 over an. You instead just take the an, but you have to take the nth root. All right. Most of the stuff is positive. It's the limit as n goes to infinity, 3 to the n over 2 to the n squared, and the absolute values can be pulled down so that they're around the x plus 2. That's a neat little trick, totally valid. Absolute values love products and powers. They can just bring them in. It doesn't quite work with sums, though. In any case, this is how you deal with the absolute value, and you do need to worry about the absolute value, excuse me, around there. Now, take the 1 over nth power before taking the limit, and you get 3 to the n to the 1 over n. 2 to the n squared times 1 over n is just 2 to the n. And x plus 2 to the n is nth root is just x plus 2. And now you have to take this limit as n goes to infinity. Well, what is that limit? That limit is 0 no matter what x is. No matter what x is, this is just a constant. I just want to remind you, that's a constant. N goes to infinity. We've just got some stuff, big number on the denominator. So this is 0 for all x, which is less than 1. Therefore, the series converges for all x. And in fact, absolutely. So a picture of the situation should have minus 2 at the center, even though it's not particularly relevant. And it converges for all x. Okay, maybe I'm kind of gypping you here. If you weren't here last time, I don't know, I haven't given you any example that has a radius of convergence which is finite or non-zero. Here, of course, the radius is infinite. There in the previous problem, I should have said that the radius is 0. But in any case, look, I'll just do one more, which I don't think I did last week. I didn't make a note of it, and I forgot to watch the video or the end of the video, but I think I did not do this one. What do I want to do? Well, maybe I'll modify one slightly from the book. Let's just do this. Okay, so it's sum from 2 to infinity, x plus 2 to the power n over n log n. How do I deal with that same sort of problem? Okay, well, ratio test again. No, it's not so easy to take the nth root of log n. Not so bad, but I'm not, I think the ratio test is easier. So I take the limit n goes to infinity, absolute value an plus 1 over an. This should be pretty automatic by now. We've been using the ratio test a lot. You've got to be able to set that up. And so too the next statement, which is just to copy on the bottom x plus 2 to the n over n log n, and then adjust on the top to x plus 2 to the n plus 1 over n plus 1 log n plus 1. All right. This is, we just do a bit of grouping. We're going to get an x plus 2 to the n plus 1 over x plus 2 to the n. But the rest of it's going to flip around, so we'll have an n over n plus 1, and we'll have a log n over log n plus 1. All right. So most of this we can drop the absolute values. If we cancel this and this, we will still have an x plus 2, which does need the absolute values. So this is the limit as n goes to infinity, x plus 2, and then the rest do not need the absolute values. So you get this. Now, I did a similar problem in regular series 2 weeks ago, where we saw by L'Hopital's rule, there you go, you get your L'Hopital's rule, that this has limit 1. But you need to use L'Hopital's rule here when you solve the problem. I'm just not going to do it because I've already done it. To do it really properly, you want to change n to a continuous variable x. N, by definition here, goes 1, 2, 3, 4, 5. So you can't really differentiate d dn. But you can change it to x, then differentiate, and you get the limit 1. In any case, this also goes to 1 quite easily, and so this limit is x plus 2, which is impervious to whatever n does. So it's x plus 2 in absolute value. And what's important is whether it's less than 1 or greater than 1. So let's examine this. So series, the power series, the one in the question, converges absolutely when the absolute value of x plus 2, which is our limit, is less than 1. And it diverges when this limit that we found, absolute value of x plus 2, is greater than 1. And I ask you to try to characterize this inequality or these inequalities more directly. This is what we would like to do. Here's the way to do it. The center is at minus 2. I want you to think of this as x minus minus 2. So this means that the distance from x to minus 2 is less than 1. So that means that we could go as low as minus 3 and as big as minus 1. Put another way, the radius of convergence is 1, because that's what's on the right-hand side here. By the way, if we had a factor out front, which we don't in this case, but we did in the last problem that I did last lecture, last review session, you have to divide by that first to get the radius of convergence. In any case, this says that x has to be between minus 3 and minus 1. So it's really useful to be able to convert this into this. And the best way that I know of is to draw a number line. And here, of course, when x is bigger than minus 1 or x is less than minus 3. So what we've shown is that the series converges absolutely in this region here. So it has a radius of convergence of 1, as I said, and diverges out here. But we have not finished the problem, because we have to check at what happens at minus 1 and minus 3. So we still don't know. I put question marks for the moment. We can come back and fill it in. So stare at that for a few seconds while I clear some board space. And we have to finish the problem by manually checking the two endpoints, -1 and -3. And you can check them in either order. You have to check them both. All right. So, we have almost settled the whole situation. Our series was, to remind you, sum from 2 to infinity, x plus 2 to the n over n log n. By the way, anyone know why I started at 2? Why not at 1? Log 1 is 0, right? You can't have 0 in the denominator. I could have started it at 0, but then log 0 itself is undefined. Not to mention that 0 would also imply 1. So you'd be screwed with the first two terms anyway. Right, so we've settled everything except what happens at the endpoints x equals minus 1 and x equals minus 3. Let's check x equals minus 1. I'm going to substitute this directly into here. So the series is, and I just replace x by minus 1. So I get minus 1 plus 2 to the n over n log n, which this is just 1 to the n, which is 1. So the series is 1 over n log n. And it's a regular series. Forget power series, think back a few weeks. How do we do that series? Can anyone remember what we did the same problem? What test did we use to do this? We used the integral test. And I am going to omit the details, but I'm just going to say it diverges by the integral test. And you need to be able to supply the details. Well, you do. Make sure you can do it. All right, so we have settled the right-hand endpoint at minus 1 to be divergent. Let's check the left-hand endpoint, minus 3. Here the series is n from 2 to infinity, the sum, minus 3 plus 2 to the n over n log n. And, of course, the numerator is now negative 1. So you get negative 1 to the n over n log n. Well, it's an alternating series. It often is at one of the endpoints, but not always. There are examples where it's not alternating at both endpoints. So the question is, if it's alternating, what's the first thing that you check? The absolute version. Of course, the absolute version of this is just up here, which diverges. And so it does not converge absolutely. Without that minus 1 to the n, if it's just a 1, it would diverge. However, with the minus 1 to the n, as we've seen, you can use the alternating series test. Again, I'm going to omit the details. Alt series test, also let's say doesn't converge absolutely because of this. Well, but the alternating series test shows it converges, and you do the details again. Therefore, it converges conditionally here. So we can now summarize the entire situation. I'll redraw this again. We're good in the middle. We're bad outside. We're bad at minus 1. And we're just good at minus 3, but it's conditional. Bad to the left. So, converges absolutely if minus 3 is less than, x is less than minus 1. It converges conditionally at x equals minus 3 and diverges when x is less than minus 3 or x is greater than or equal to minus 1. By the way, I do have a correction to last week's video that occurred to me. The very last thing that I wrote in that example, if you watch it or if you were here, maybe in your notes, I think I wrote something like converges when 6.5 is less than or equal to x is less than or equal to 7.5, or converges absolutely there. And then I also said it diverges at 6.5. This was wrong. I shouldn't have had the equals there. I just meant to write less than in both cases. So please make that correction. It should have been less than. both cases. All right, so we finished the problem. You see, that one is more involved because the radius of convergence is neither 0 nor infinity. In that case, you have to check the endpoints individually. By the way, just looking at this again, suppose I changed it slightly. I put a ghostly version of it so that there's a 2 there. So I'm squaring the log x. That's a worthwhile problem to just repeat all the steps of this problem yourself with this new problem with the square there. You will find that there's not a lot of difference. The ratio test part works out the same. The only difference is the endpoints will have a log n all squared. And in this case, the series converges by the integral test. You have to try it and see. But the squared makes all the difference. If I had a log n all squared, a different version of the problem, this would converge. So then what would you do in this case? For the other endpoint, you'd have log n squared. Well, the difference would be that the absolute version would converge, and you would not use the alternating series test in that case. The details are actually written up in my book, and I'll give you a reference for that, since I'm kind of skipping over them pretty quickly. It's 26.1.2. 26.1.2. And in any case, you find it converges absolutely at both endpoints. So you really do have to check those endpoints with some care. All right. That's what I want to say about radius of convergence. Any questions? Yes?
What if you had made the x plus 2 what if you made x plus 2 to 2?
You mean...
With an x plus 2 squared.
So you're saying if the top had been x plus 2 to the 2n or to the 2n? Okay, so then you would end up, so I presume that you want the bottom to stay like this or something?
Yeah.
Okay, so that's a power series where you're only going to get even powers. Right, now when you do the ratio test, the ratio would now be x plus 2 squared. You don't need absolute values in this case because everything is positive. That would be the limit. And what you're interested in, again, though, is this less than 1 or greater than 1? And so if you take the square root of the thing, you're actually in a very similar situation to the way you were before. The real difference in this problem actually turns out that it would be at the endpoints. If you plug in minus 1, you get 1 to the 2n, which is the same. But if you plug in minus 3, which is the other endpoint, here, x equals minus 3 would give you the sum of 1 to the 2n over, minus 1 to the 2n, rather, over n log n. Now, what is that? What is negative 1 to the 2n? Is that alternating? No. If you take negative 1 to any even power, you get 1. So actually, this is an example where it's not alternating at either endpoint. In this case, the right-hand endpoint, x equals negative 1, it's obviously this, but the left-hand endpoint is the same. So that's a bit of a trick. And what you will find in that case is that it diverges at both endpoints. You don't get that conditional convergence there. So that's how this would be modified. Any other questions before I go on to the next topic? Well, if you have one, this is a good chance to shout it out anyway. Well, it's not that I don't want to show you why that diverges. What I want to do is refer you. The question is, I don't want to show you why it diverges. I kind of feel like I've already done it. So, I'm sorry? Which chapter? I think that you will find it. 26, 25, 24, 23, I believe. You'll find it in there. It's the how to solve sequences in series problems. Look under integral test, and it's probably the first example there. That's probably easier than trying to look at the video from a couple of weeks ago. Although, you know what? It's right at the beginning. That's the first thing I do, I believe, 2 weeks ago. So that's another reference to it. All right. Next topic. I call this How to Get New Series from Old Ones. And it's in 26.2 of the book. How to get new series from old ones. Well, in order to get old ones, we have to have some series. And we've seen a few. I want to catalog the ones we've either seen or are very close to the ones we've seen. And I consider these series to just know. So here are 5 series, really 5.5, that I think that you should just know. The first is the series for e to the x. In sigma notation, it looks like this. Written out, it's our old favorite. This converges to e to the x. Maybe I'll write this on the left side. Let's do it like this. E to the x equals. So this is a series for e to the x. All of these are Maclaurin series, by the way. Remember, Maclaurin means Taylor with a equals 0. So you're dealing with x to the n, not x minus 3 to the n or x plus 7 to the n. It's just x to the n. All right. Whenever you write down a series like this, you also need to say where it converges, and in this case, for all x. So again, if I plug in any value of x and replace it by, say, 10, I get an equation. E to the 10 is 1 plus 10 plus 100 over 2 factorial plus 1,000 over 3 factorial, and so on. So that means it's convergent series, and it converges to e to the 10. And that's true no matter what you replace x by. We'll change 10 into. We also have a series for sine x. Or do I prefer to do cosine x first? I prefer to do sine x. Very good. I might as well be consistent with my book, although there's no reason to learn these in an order. In sigma notation, it looks like minus 1 to the 2n plus 1 over 2n plus 1 factorial x to the 2n plus 1. So it's just the odd powers starting with x minus x cubed over 3 factorial plus x5 over 5 factorial minus x to the 7 over 7 factorial and so on. And this, again, converges for all x. It has an infinite radius of convergence. Okay, sine is an odd function. There are odd powers. That's the way to remember it. As for the alternation, you're pretty much on your own. I cannot tell you how to remember the alternating aspect of it, but it just does. Okay, cosine x is very similar, but it's an even function. You only get the even powers, so you have minus 1 to the... This is dumb. This is dumb. I've done something dumb. There's an n here. Ouch. There's an n here too. I was going to write 2n, but of course that would always just be 1, so that would be dumb. I hope I didn't make that mistake in my book. Anything's possible. Right, so when you write this out, you get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Again, alternating, and only the even powers, and this is also true for all x. By the way, if you differentiate any of these terms, you get, or all of these terms, you get this. Derivative of x is 1. X cubed over 6, derivative is x squared over 2. X to the 5 over 120, x to the 4 over 24. Try it and see. It's kind of nice. It's kind of nice. So, of course, the derivative of sine x is cosine x. I'll talk more about differentiating power series in a little bit. I've got to give you the 2 other series. The 4th one is the geometric series. This is a series for 1 over 1 minus x. And that is the sum of just x to the n. Simplest power series you can possibly write down. It's just got all coefficients 1. And so on. But this is only true for x between minus 1 and 1. The ratio has to be between minus 1 and 1. All right, so we've seen that one before. Here's one we haven't explicitly seen. You can get it just by differentiating this series. I'm sorry, you can get it by integrating this series, but more on that in a second. Log of 1 minus x is equal to the sum, and we better start from 1 to infinity, and you actually get minus x to the n over n. Doesn't have a factorial, funnily enough. So this is minus x squared over 2, minus x cubed over 3, minus x to the 4th over 4, and so on. So they're all negatives, all the terms. And this is only true, again, for x between minus 1 and 1. Actually, it's true also x equals negative 1. That's sort of weird. Let me say the other one that I think you should learn together with it, although no matter which one you learn, you can easily get the other. If you want log of 1 plus x, you put a negative 1 to the n plus 1. It's alternating now. So it starts off positive. It's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. And again, this is true when x is between minus 1 and 1, and it also happens to be true when x equals 1. Now, just to sort of a real aside, not in the course, when x equals 1 in that bottom series, you get an expression for log of 1 plus 1, which is log 2, which is 1 minus a half plus a third minus a quarter plus a fifth minus a sixth, and so on. That's that funky series that is alternating where I go 1 forward and then a half and then a third forward, a quarter. I've demonstrated this before, much to your, well, cringeworthily. But it turns out to converge to log 2. The reason why it's tricky is because it doesn't converge absolutely, and so this is not really in the course, but it's kind of nice. It's kind of nice. In any case, there you see 5 and a half. There's really 2 at the bottom there, but there's 5 series which I think you just need to know. So those are our base series. So given them, what I'd like to do is explain how to use them to brew up some new series. And there's a bunch of different techniques, the most useful of which is substitution. So let's look at this first. Substitution. If you have a series, you can substitute in a power of x, or perhaps even a multiple of a power of x to get a new series. For example, how would you get a series for e to the x squared? Well, take the series for e to the x. You can do this in either sigma notation or written out. I'll just write it out. So we have this for all x. So you replace x by x squared in here, and you get e to the x squared is 1 plus x squared all squared over 2 factorial plus x squared all cubed over 3 factorial, and so on. Also true for all x. It's true for all x squared, therefore true for all x. And so the powers actually jump up by 2 every time. I don't know if that's enough terms to get the picture, but hopefully it is. If you did have to write it out in sigma notation, you could start with the original sigma notation and replace x by x squared, or you can just inspect this and say, look, the denominator is n factorial, but the numerator must be x to the 2n. It's sort of obvious just from looking at it. And it's true for all x. Okay, that's a pretty easy one. How about this? 1 over 1 plus 2x squared. Well, I look at this and I say, which one of my standard series does it look like? Well, clearly the fourth one, the geometric series. Problem is, it doesn't really look like it. It almost looks like it. I'm going to have to think of this as 1 over 1 minus quantity minus 2x squared. Then it looks like it. So if I start off with, I don't really have enough room over here. I'd better move over. No matter how one plans these things, somehow there's never enough room. Right. So I'm going to start with the geometric series. And as I write it, I'm going to be very careful to specify where it converges. After all, that was the subject of the first half hour, and I haven't abandoned the idea of worrying about this. So I start off with this series from the right-hand board, and so on, and of course that converges when x is between -1 and 1. So what we've seen is we have to replace x by -2x squared instead. And so we get 1 over 1 plus 2x squared is equal to 1 minus, well, let's do it like this, 1 plus -2x squared plus -2x squared all squared plus -2x squared all cubed plus ... This is true when -1 is less than -2x squared is less than 1. You must also replace the x in the inequality, or else you will run into all sorts of problems. All right, so we simplify this. It becomes alternating. 1 minus 2x squared plus, well, we can write 4, 2 squared x to the 4th, minus 2 cubed x to the, I left out the 2 here, so it's 6, and so on. And in sigma notation, while I'm on the topic, this would look like -1 to the n, because it's alternating. We'll have an x to the 2n, and there's no fraction. There's just a power of 2. So it's 2 to the n minus x to the 2n. Man, really struggling with this. And you could also write that as -2 to the n, actually. X to the 2n. That would be a little tidier. But we have to come back to this inequality and manipulate it a little bit. I don't really care what -2x squared is doing. I kind of want to know what x is doing. So first of all, it doesn't matter. You can multiply both sides by this or all three sides by -1. If you do, you get 1 greater than 2x squared greater than -1. In fact, 2x squared, x squared has to be positive. So actually, we have x squared is less than 1/2 will do. I mean, you could also put greater than -1/2, but of course it's greater than -1/2. The interesting thing is that the solution to this becomes symmetric once again. X is between 1 over root 2 and -1 over root 2. It's a common mistake, by the way. Solve the inequality, x squared less than 4. Oh yeah, it's x less than 2. No. -2 less than x less than 2. In this case, we have a half instead. And so this is where the series converges. So we have gotten a series for the object that we're looking for, and we have said where it converges. -1 over root 2, less than x, less than 1 over root 2. We don't need to use the ratio test method to show that this converges in this area. We could use it, but we don't need to because we've already analyzed the situation for the geometric series. Why reinvent the wheel? Why mess around with the ratio test and all that? We know everything we want to about the geometric series. This is just a different geometric series. The ratio is just different from what it was. All right, so that's the idea of substitution. Take a series you know and substitute in some other power of x or multiple thereof, and don't forget to check where it converges. Does anyone have any questions about that? All right, let's move on to the second thing you can do. 2. You can differentiate a power series, and the new series you get will have the same region of convergence as the old one, except possibly the endpoints. So a sort of simple, classic example of this is to get cosine from sine. And I've sort of already talked about that, and you might as well try it yourselves, but I kind of want to just try to get a series for something that's not on our standard list. 1 over 1 plus x all squared. This is a bit of a pain to differentiate, and it's not directly actually from any of our series, or at least you don't get it by substituting one of the classic series. The way that I would get this is to start with 1 over 1 plus x. And that's almost the same as one of our series. I'm going to consider it's a geometric series, but it's got a minus x instead. And so the difference will be, it'll be an alternating geometric thing here. So the ratio is minus x, and so on. And this is true when minus 1 is less than x is less than 1. All right. So if I differentiate both sides, the derivative of 1 over x is 1 over x squared. So if I differentiate this, minus 1 over x squared. If I differentiate this, I get similar thing, minus 1 over 1 plus x all squared. And then, don't worry about that interior step. Now I just have to differentiate this term by term. This is a nice fact. It's not obvious that you can differentiate an infinite thing term by term, but it turns out that you can within the radius of convergence. Beautiful, but needs a proof? Well, I'm not going to give you one. I wish I had time, but I don't. This is also going to be true for the same values of x. The differentiated series inherits it, but maybe also the boundaries. You know, that's where you'd have to check at least that the right-hand side converges or diverges. In this case, it's pretty easy to see when you plug in, say, 1. You're going to get minus 1 plus 2, minus 3 plus 4. It's not going to converge. The nth term test will fail. Same with minus 1. It's not convergent at either endpoint. So in this case, no problem. There are actually some theorems about whether the differentiated series converges if the other one doesn't, and the same with integration, and I'm not going to get into that. The point is we've got almost the series that we want. We just have to multiply both sides by minus 1, and we'll get 1 over 1 plus x all squared as the series 1 minus 2x plus 3x squared minus 4x cubed, etc., which we can write in sigma notation as n plus 1. Well, maybe I'll put the negative 1 to the n. It's alternating first, so it's negative 1 to the n. And it's n plus 1 times x to the n. And this is true for minus 1 less than x less than 1. All right, so we've got differentiation. Sometimes this is very useful. It doesn't seem to come up all that often because, I don't know, there's not that many series that you get out of differentiating. Probably if you look at the standard ones there. See, if you start with, for example, this one, or this one, and you 5, and you differentiate it, you get 4. It's worth trying. Kind of nice. In fact, you can almost see it just by inspection. If you differentiate this, minus x becomes 1. Minus x squared over 2 becomes x. Minus x cubed over 3 becomes x squared, except with the minus signs on the front. But when you differentiate this, you get another minus sign by the chain rule. That's something to try. Anyway, that's all I have to say about differentiation. I'm kind of whipping through these techniques pretty quickly because there's lots of them. Any questions about it? Yes? Sure. Power series for log x. Okay, that's a good question. This actually belongs more in the first thing, substitution. So let me rewind. No, it's fine. It's fine. I like questions about what I've done in the past. Easier to answer than things that I will do in the future, since I never know exactly what that will be. In any case, so the question would be, what about a series for log x, for example? Now, the thing about log x is that it is not defined at 0. So you can't find a Maclaurin series for log x because x is not 0. But suppose that you were asked for a series for log x about x equals 1. Well, if you start off with log of, say, 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on, which is valid, as we've seen, for x between minus 1 and 1. also add x equals 1, but let's not get bogged down in that detail. Now, suppose I set, for example, y is equal to x plus 1 in this equation. So that, to be concrete, x is y minus 1. I will get log of y, after all, y is the same as x plus 1, is equal to y minus 1 minus quantity y minus 1 squared over 2 plus y minus 1 all cubed over 3 minus y minus 1 to the 4th over 4, and so on. And that's valid. Remember, x is equal to y minus 1. So that's valid when minus 1 is less than y minus 1 is less than 1. And if I add 1 to all three of these quantities, I get 0 less than y less than 2. Look at this. You will see it is a power series for log of y, and the center of the power series is 1. All the terms are powers of y minus 1. So this is exactly the series that we're looking for. Now, here's a question. Could you use this to get a power series for log of y about y equals 7? Can't you use the same technique to do it? The answer is no. If you try this trick and you say, oh, I want this to be powers of y minus 7. So you replace x here by y minus 7 instead. You would get powers of y minus 7 there, but on the left-hand side, you get 1 plus y minus 7, so you get a y minus 6. So you wouldn't have log y on the left, you'd have log of y minus 6. So there's only so much you can do about this translation. If you plug in, instead of a power of x, x minus something, or x plus something, you will get another power series. You will shift the center, but unfortunately you also change the function. In this case, the function is log 1 plus x, and in this case, the function is log y. So you're dealing with two different functions here. This is x equals 0, this is y equals 1. So you can't get something for nothing. If you know a power series at a certain point, you cannot find that same function's power series at any other point. If you plug in x minus a, you can get a power series about a instead, but it will be for a different function. Like this and this. All right, that's a good question. In fact, to tell you the truth, I had meant to address a very similar issue, or basically the same issue, and forgot. So, thank you for bringing it up. All right, so moving on, though, to the third technique. We've differentiated. You can also integrate. So you're allowed to integrate a series term by term. And that is actually the way to get the log series number 5, which I'm just erasing. You start with the geometric series, integrate it term by term, and that's how they probably got the log series in the very beginning. Now, here's one that's a little more exotic. How would you find a Maclaurin series for inverse tan of x? Inverse tan of x. Well, you could differentiate it over and over, but that's a pain. Instead, write it as an integral of 1 over 1 plus x squared dx. So we're going to need a series for 1 over 1 plus x squared. Not long ago, I did the same series with a 2 there. So this is actually even easier. And you find, without much ado, I'll have to leave it to you to check these details. You don't get powers of 2, but you do get alternating, and you do get only squares, even powers there. And this is true for x between minus 1 and 1 again. So there's some details for you to check there, but as I said, I more or less did it. So if you integrate both sides, you are allowed to integrate term by term through the integral. Again, that's a nice little fact. And you will get then x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7, and so on. What did I forget? Plus c. Unfortunately, it's kind of silly to put plus c at the end of this because it never stops. There is no end. So I will put it at the beginning, where it belongs, the constant term. So c plus, not plus c. Okay, so this is, of course, inverse tan x, arc tan x. So up until the first term, just the constant term, we found the series. But you must find the constant term. And the way to do this is to put x equals 0. If you put x equals 0, you get arctan 0 is equal to c plus 0 minus 0 plus 0. Well, there's a c here. Power series have a constant term. If you integrate something, then the first possible term will be x. There's no constant term in the series. That's what the plus c is. So if you differentiate this, you will get this, regardless of what c is. Right? If you differentiate a constant, the c goes away. The constant goes away. So you have to find out what it is. Right? So we plug in 0 into this equation, and you get inverse tan 0 is 0. So in this particular case, the constant is 0. And you get the series for tan x. X minus x cubed over 3 plus x to the 5 over 5 minus x to the 7, and so on. And this is, in sigma notation, minus 1 to the n over 2n plus 1 x to the 2n plus 1. Same as the series for sine x, right? What's the difference? What's the difference between this and the series for sine x? Yeah, the sine x has factorials. This does not. Makes quite a big difference. This is actually more like the series for log, in that there's no factorials, which is not actually a surprise if you do your complex numbers properly, but I'm certainly ahead of myself here. All right. Are you happy with this plus c? Okay, good. So there's an example of integration. Any questions about it? About the idea? All right. Let's move on to another technique. And my paper's over there. So I'm going to guess that what I was going to talk about is adding power series. You can add and subtract power series term by term. Within the radius of convergence. As long as you work where both of the series converge, everything is fine. So, as an example, what would the series for sine x minus e to the x be? Well, you just write sine x as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And then, in this case, I'm subtracting the series for e to the x, 1 plus x squared over 2 factorial. One caveat is you must make both of these series go up to the same order. So in this case, I have to go up to x to the 4th and x to the 5th. It is no fair doing one up to some order and the other into a different order. In this case, the x to the 5 over 5 factorial is going to cancel out. But if you couldn't be bothered writing it over there, you might think that it does not cancel out. Actually, you could write out one more term, x to the 6th over 6 factorial here, if you wanted to, because this series here, I've written it out up to order 5, but you can also think of this as being order 6. So there is no x to the 6th term. The next term would be x to the 7 over 7 factorial. So this is, you can't tell whether I've written it up out to order 5 or order 6. So let's just say I do it to 5, so that I have to write out an extra term here. And you will see that you get negative 1. The x's cancel out. You'll have a minus x squared over 2 factorial. This is x cubed over 6, but it cancels out with this one here. No, it doesn't. It is an extra minus. So it'll be x cubed over 6 minus x cubed over 6. So x cubed over 3. I'll drop the factorial here, actually, since 2 factorial is 2. I'll have a minus x to the 4th term over 4 factorial, which is 24. And the x to the 5th term goes away. They cancel. And this is true up to order 5. Problem is, there's no easy sigma notation unless you combine the 2 sigma notations. So, I don't know, probably the question would say, what is this series, Maclaurin series for this up until order 5? And this would be the answer. Up to 5th order. So normally, I guess the question would try to specify it, in which case you must write out both series up to that order and then cancel everything out and see what you get. Question?
Would you say up to order 5 the first 5 terms?
No, that's actually a good question. What they mean is, if they say up to 5th order, then, so the question is, for the record, is it the same as if they say the first 5 terms? And actually, the answer is no. In this case, up to 5th order means you write both series to include degree 5 or less. And then you write down the answer. Okay? However, it is possible for them to say the first 5 non-zero terms, in which case you cannot guess what the order is. In this case, you would write this out and say, oh crap, I've only got 4 terms. I need more. I need more. I need one more. So then I would write in the x to the 6th over 6 factorial here. There's nothing to write there because the 6th degree, as I said, is 0. But then you would have a minus x to the 6th over 6 factorial, which would be the 5th non-zero term. So, yes, that permutation is more difficult.
Does it matter if the series starts from n equals 1 or from n equals 0?
Does it matter if the series starts from n equals 1 or from n equals 0? Look, you know, I wouldn't even think about what n is. I would just write out the terms until the degree that I was interested in. So you pick a degree. In this case, I picked 5. And then I saw what I got. And if I needed up to order 5, I would say, okay, I'm done. There is no 5th order term, so I'm done. On the other hand, if the problem did say, what are the first 5 non-zero terms of this e to the sine x minus e to the x, I would have to include this x to the 6th minus 6 factorial term. And I wouldn't have known that in advance. I would have done what I did and then said, as I say, oh crap, I need an extra term or 2. So write out more than you need. If you have too many terms, you can always cross one of them out and change it to plus dot dot dot. But the thing that's critical is that they must both match order. You cannot write an order 3 thing here and an order 7 there. They have to be the same order. They do not have to be the same degree, because as I've discussed, sometimes that leading term is 0. There's no 6th degree term here, and yet there is a 6th order. It's the same as this 5th order. Okay? So these permutations are annoying, but they do come up. All right, so adding and subtraction is easy. You can also multiply them together, and that's a bit of an art form in itself. Now, suppose that I want e to the x times sine x, and let's ask for the first, 4 non-zero terms. What the hey? So, what I'm going to do is I'm going to write out the series here, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I don't know how far I have to go. Let's just try this far. Times sine x is x minus x cubed over 3 factorial plus, well, you know what? I cannot write x to the 5 over 5 factorial there, or else I should have written it over here. I've got to match these things. Maybe you think I should match them, but I'm going to be ambitious. I'm going to try 4th order here. If I am lucky, then I will have 4 non-zero terms. Actually, I could have 5 non-zero terms if I'm really lucky, because 4th order is 0, 1, 2, 3, 4. 4th degree polynomials actually have 5 coefficients. So if I'm really lucky, then I will get 5 non-zero terms. You know what? Let's just see if it works. Okay, here's the tactic. This is a 4th order. This is a 4th order, even though it only goes up to 3. So my tactic is quite straightforward. I am going to only concentrate on terms where the degree is 4 or less. So if I were to multiply this out, I would say x times 1 is x, fine. X times x is x squared. X times x squared over 2 factorial is x cubed over 2. X times x cubed over 3 factorial is x to the 4th over 6. I'm expanding out the 3 factorial. But x times x to the 4th over 4 factorial is x to the 5th. And that's already higher than my focus. I've decided to focus on 4. So guess what? I don't write that term. Now let's deal with this. This times 1 is x cubed over 6. And this times x is minus x to the 4th over 6. However, this times x squared, already x cubed and x squared is x to the 5th, x to the 6th, x to the 7th. You know what? It's too high. And so I ignore those terms. There's a real art into only using the terms that you need. Now, here is the bad news. When I write it out, I get x plus x squared. This term and this term together become plus x cubed over 3. Unfortunately, I've had a run of bad luck, and the x to the 4th term goes away. The x to the 4th terms cancel out. That is unfortunate because what it means is 4th order is not good enough for the problem. As stated, the problem was I want all the terms, I want 4 non-zero terms. I have got the terms up to 4th order, but that's not good enough. I'm going to have to go up to 5th order at least. So I start again, I'm afraid, although I won't have to duplicate everything because the first 3 terms there shouldn't change unless I've made a mistake. So let's repeat. We gnash our teeth saying, damn, we were too optimistic. We wanted 4 non-zero terms. So let's go up to 5th order. Let's try again. Up to 5th order, here's what I get. E to the x sine x is 1 plus x squared over 2 plus x cubed over 3 factorial is 6. X to the 4th over 4 factorial is 24. X to the 5 over 5 factorial is 120. Okay. That times sine only has x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And if we're lucky, this is going to work. Man, I hope we're lucky. So, again, I'm going to do the x term first, only going up to terms of order 5. I get x plus x squared plus x cubed over 2 plus x to the 4th over 6 plus x to the 5 over 24. And I do not bother multiplying the x by the x to the 5th, because already that is a degree 6, and 6 is higher than my focus of 5. So now I move on to the x cubed over 6, and I start multiplying. I get negative x cubed over 6, negative x to the 4th over 6, negative x to the 5th over 12, but then I stop because 3 and 3, the degrees there give me 6, 7, 8, too high. Gone from my focus. X to the 5th over 120, I will have one term there, but x to the 5th times x is already x to the 6th, 7th, 8th, 9th, 10th, and that's the only term that matters. So I have selectively ignored. It's basically multiplying out 2 polynomials, but you never write down the terms which are going to have x to the anything bigger than 5. Okay, so that's the only difference between this technique and the regular thing, and it's kind of nice. Normally you'd have 6 terms, 3 terms there, 18 terms, but here we only got half that many. Anyway, what do we get? Well, we still have x squared over 3, x squared over 2, x cubed over 3. The x to the 4th terms cancel out, but now the x to the 5 terms do not cancel out. We have 1/24 plus 1 over 120 minus 1/12. x to the 5. So how many is that? It is 5 minus 10 plus 1. So that's minus 4 over 120, which is minus 1/30th. And so I believe minus x to the 5 over 30, and so on. And there are the first 4 non-zero terms of that product. So had I just been less ambitious or greedy or whatever you want to call it, and started with the 5, I could have saved myself everything I did on that other board. That was just, I had to stop. Question? Yes, sorry, that's just my bad. Yeah, x squared, x cubed, yep, okay, that was a mistake, thank you. I got it right on the other board. All right, any questions about that? Okay, so that's multiplication for you. Unfortunately, it is possible that you might get a division problem, and there you have to bust out a long division. And I kind of don't want to do much about it. I'm going to do a really straightforward division question, just to emphasize, well, just to illustrate, how would you get a series for tan x up to third order? That's all I'm going to do. Third order. It's kind of nice to do higher order for this, just to practice, but it'll take too long. So tan x, I can't get it by substituting or doing anything clever. It doesn't seem to fit any of the other categories. I'm going to consider tan x is sine x over cosine x. So that means I have to divide cosine into sine x. Okay. Well, that means that I've got to do cosine x into sine x. How many times does cosine x go into sine x? Well, cosine x up to third order is 1 minus x squared over 2. And sine x is x minus x cubed over 6. That's all it is up to third order. So let's just do the long division. How many times does 1 go into x? X. Multiply these two, and I get x minus x cubed over 2. And so on. So if I cancel this out, I get x cubed over 6 minus x cubed over 6 plus x cubed over 2. So it's x cubed over 2. So let's see. How many times does 1 go into x cubed over 2? Once. X cubed over 2. And if I do multiply this out, I'm going to get x cubed over 2 plus higher order terms. Notice again, I'm not concerned about anything above degree 3, so I kind of chop everything off and I'm down to 0. Of course, there's a huge remainder. It's all of the rest of the terms, but I don't really care what they are. So I've proved that tan x begins x plus x cubed over 2, and so on. Now, as I said, it's more illustrative to go up to higher terms, but it would just take a little too long. Why did I say x cubed over 2? Can I not do arithmetic here? I cannot do arithmetic. I said one thing, actually, and wrote down another. Minus a sixth minus minus a half is a third. Oi. I'm sorry about this. Can you please, Mr. Cameraman, focus on all of this and notice that somehow it's all x cubed over 3, not 2. Or at least this one is a 2, but the rest of them are 3. And so, I don't know what happened here. Just a brain drain. All right. So anyway, it's worth practicing a few of these long divisions. It's just polynomial division, but you ignore everything after a certain column, and I guess you also write things in reverse order. You start with the lowest degree rather than the highest degree, and everything works out. So practice it. Anyway, these things come up once in a blue moon, so I don't have much else to say about that. Now, what other tactics do we have? We have run out of lecture notes. We've also run out of tactics. That's it. Those are the tactics of getting new series from old. Okay, so they're all worthy of practice, and it's not clear always which one to use. So you kind of just have to be aware of the tactics, and there are some common questions, and see if you can get something from one of the existing series by a substitution first, and then try other things like the differentiation, integration, or one of these arithmetic operations. All right, I move on to the next topic, but first, anyone have any questions? A stony silence. All right, very good. So, I'd like to move on to section 26.4, but actually only after I do 26.3. So, this problem, this type of problem, I'm getting very close to the end of power series, and hopefully I have a little time to talk about complex numbers. There is a type of problem which involves taking a derivative of a function, but not just a derivative, an nth derivative where n might be very large. So as a sort of classic example, let f of x be e to the x squared. Is that the example I want, or e to the x cubed? No, e to the x squared will do. And the question is, what is the 100th derivative of f at 0? And what is the 101st derivative at 0? Well, method 1, differentiate e to the x squared 100 times. If it was just e to the x, you wouldn't mind it so much, right? I can do that. 100th derivative of e to the x is e to the x. Unfortunately, even the first derivative requires the chain rule, and you get 2x e to the x squared. Then you have to use the product rule and the chain rule. Then the next time you have to use the product rule and the chain rule twice, or at least the product rule twice, and so on. And it becomes an unbelievable cascade. And then you just have to plug in 0 at the end. So clearly this is not the way that you should do this problem. Here is the way you should do the problem. We've got to reverse engineer our Taylor series. So, very often we have a function f, and we've said that f of x equals its Taylor series. Now this is not always true, but for a lot of functions that we've looked at, like all the ones we've been doing in the previous examples, f is equal to its Taylor series, at least where it converges. I want to emphasize, this is not true for every f. There are examples where this is just completely false, but they're a little bit exotic. They're a little bit exotic. For most of the types of functions that we've been looking at, this equation is true, at least in some region. As I said, all of the ones we did in the previous topic fall into that category. So if this is true, well, even if it's not true, if this just happens to be the Taylor series, so if f, so maybe I should say, if f has Taylor series, so it doesn't matter whether it converges to it or not. If you know the Taylor series, then this is the coefficient. So actually, if you know the coefficient, you can find the derivative. So the coefficient an is this. So we have an is the nth derivative of a over n factorial. So that means that the nth derivative at a of a function is n factorial times an. So what does this mean? This means that, okay, in the previous ones, we've sort of known the derivatives. Well, last week we did a lot of examples like this. We know the derivatives, and you get the Taylor series. Here, imagine you know the Taylor series. Then that gives you the derivatives. We're sort of flipping it around. So what I want to do is I want to take this equation here and write it out in words and put a box around it. The hope being that the box will remind you to remember what is inside the box. Do not think outside the box in this particular case. It is inside this box that I want you to learn. So I'm just going to write this out in words once I get some space. And then we'll use it to solve this problem. So what are these words? Well, it depends on what you consider an to be. I consider it to be the coefficient of in the Taylor series. So here it is, in words. The nth derivative of any function at some point a is equal to n factorial times the an. And the an is the coefficient of x minus a to the n in the Taylor series of f about x equals a. And here is the box. Okay, so what it suggests is if you can find a Taylor series, then you can find the derivative, at least at the center, when evaluated at the center of that Taylor series. How do you find Taylor series? We've just spent 45 minutes doing it. So in our example, f of x equals e to the x squared, we got the Taylor series for it by substituting in x squared instead of x into the standard one we already knew. So we have e to the x squared is this, and it happens to be true for all x, although it's totally irrelevant, as I said, where it converges in this case. So the 100th derivative, luckily this is a series about x equals 0. So here a equals 0 in this series. So we can find the derivatives only at 0. Cannot use this to find f 100 of 1 or minus 12 or anything like that, only at 0. But this is going to be 100 factorial times the coefficient of x to the 100 in this. That's the Taylor series about x equals 0. Well, what is the coefficient of x to the 100? There's two ways of finding it. One is to write out the series until you get to x to the 100, and then see what the coefficient is. The other is to intuit the pattern and realize that the x to the 100 term is going to be x to the 100 over 50 factorial, because after all the even terms have half as much factorial on the bottom. So this is 100 factorial times what's outside the x to the 100, which is 1 over 50 factorial. So there you get 100 factorial over 50 factorial. And that is the answer. Please do not write this as 2 factorial. It is not 2 factorial. Okay, to show you how different it is from 2 factorial, just consider the top is the product of all the numbers from 1 up to 100, including 50 and 51 and 52 and so on up to 100, whereas the bottom is just the product of the numbers from 1 to 50. And so when you cancel out, you get a humongous number of 51 times 52 times 53 and so on up to 100, which I hope you'll agree is quite different from 2. So this is not 2 factorial. Anyway, you don't have to write this part out. I just want to give you an idea of how big it is. This is a perfectly acceptable form of the answer. Yeah, question?
How did you know that you're supposed to use the term x to the 100?
Because the question asked for the 100th derivative, and my formula in the box up there says that to find the 100th derivative, I ought to take 100 factorial times the coefficient of x minus a to the 100. Here a is 0. Okay, now the second part of the problem, so the question was, how did I know to use the 100th derivative? So the second part of the problem is to find the 101st derivative. So this is 101 factorial times the coefficient of x to the 101 above. Okay, so again, I want the 101st derivative. That's why I'm looking at the coefficient of x to the 101. Now, if I come back up to the series, the next term is 102 over 51 factorial and so on. What is the coefficient of x to the 101 in that? It's 0. It does not appear. You only get the even terms, even degree coefficients, are non-zero. And that's not surprising, actually, since e to the x squared is an even function. In any case, this is 101 factorial times 0. So that derivative is actually 0. Kind of neat, huh? Oh, man. All right. Any other questions about that example?
Can you explain how come there's no,
You mean, why is there... Okay, so the question is, why is there no x to the 101 term? Well, if you write out the series, as I've done here, you'll see you only get the even powers of x. It's an even function, e to the x squared. I took the series for e to the x. I plug in x squared, and all the odd powers go away. So that means all the odd derivatives at 0 are actually 0. Same is true of the first derivative, the third derivative, the fifth derivative. Just happens like that. Question?
So when you have x to the 100 over 50 factorial, isn't that only the 50th derivative since you're squaring?
Aha. So the question is, wouldn't you get the 50th derivative from there since it's the 50th term? This is the 50th non-zero term.
Right.
Surely this gives you the 50th derivative. But it's not. If you differentiate this 100 times, just differentiate that 100 times. The first will be 100x to the 99, then 100 times 99x to the 98, then 100 times 99 times 98. You see where these factorials are coming from. If you differentiate this 100 times, you get 100, then 99, and 98, and they all become products, and you'll have 100 factorial in the end. All of these ones will go away, and all of these ones will still be higher, but then we plug in x equals 0, and so actually you can almost see it just by differentiating both sides of this 100 times. So yeah, actually it doesn't matter that it's the 50th non-zero term. You actually do get the 100th derivative. Because it's that power x to the 100 that needs to be differentiated 100 times before it becomes a constant. If you differentiate this exactly 100 times, it's constant. If you differentiate it more, it goes away. If you differentiate it less, you have an x, and then like a power of x, and when you plug in x equals 0, it also goes away. The only thing that it's impervious to, or that it survived, is 100 derivatives, by which time it has spat out 100, 99, 98, so-and-so, which is the 100 factorial. It actually makes a lot of sense if you look at it that way. All right, better do one more example. Sometimes these things come in sigma notation. So if I just define a function for you by a series, suppose I define f of x is sum minus 1 to the n plus 1 n cubed x minus 6 to the power 3n all over n factorial. That defines a function. And actually it makes sense for all x as it turns out. You'd have to use the ratio test to really nail it down. But the n factorial on the bottom grows very quickly, quicker than anything on the top. So if you tried the ratio test, you'd find that this makes sense for all x. Not that it matters, because all I'm interested in is what is the 300th, I believe? Is that what I want? Yes. What is the 300th derivative of this bizarre function at x equals 6? And what is the 299th derivative at x equals 6? Well, you don't need to find a series for it because it already is a series. So to get the 300th derivative at x equals 6, all you need to do is realize it's 300 factorial times the coefficient of x to the 300 in the series. Now, here's where you've got to be careful of your n's. If you plug in n equals 300 in there, which is definitely a term, what power will you actually get? You'll get 900. So, which value of n do we actually need to get 300? You need 100. So, i.e., 3n equals 300. So n equals 100. Well, if I plug in n equals 100, I still got the 300 factorial, of course, but for n equals 100, I get minus 1 to the 101 times 100 cubed over 100 factorial times the x minus 6. Ah, man, I wrote x to the 300. Of course, it's x minus 6 to the 300, since the 6 is where I'm evaluating the derivatives. Notice that this is a power series about x equals 6. So I can't find any information except at x equals 6. Anyway, the crucial thing is that you get this expression with the hundreds here, not 300s. It's wrong to put 300s there. That would give you the coefficient of x minus x to the 900. It's worth tidying it up a little bit. It's minus 1 to the 101. So you get minus 1 times 100 cubed over 100 factorial times 300 factorial. And if you want to be really stylish here, you cancel out one factor of 100. And you get minus 100 squared, which is 10. Well, I'll leave it as squared, over 99 factorial times 300 factorial. You see, if I take 100 factorial and I cancel out 100, I'm still left with 99 factorial. All right? How about the other part? F to the 299, I believe, at 6 is 299 factorial times the coefficient of x minus 6 to the 299 above. Okay, so the question is, what n can you plug in to get a power of 299? Yeah, well, you'd have 3n equals 299. So that means that n is 99 and 2/3. Can n be 99 and 2/3 in this series? No. N is 0, then 1, then 2, then 3, then it goes to 99, and then it skips 99 and 2/3. It just goes to 100. You only get actually powers which are divisible by 3. So the power before the 300th will be the 297th power. The other terms are not there, so they have coefficient of 0. So again, this is 299 factorial times 0, and the answer is 0. Sort of similar to the other case. Question? So the question is, why can't we just use this method to find the 300th derivative of f at x? Like this. I'm afraid that is very tricky. That is very tricky. In this particular case, it's not that bad, but it's pretty nasty. You would actually have to differentiate this 300 times to see what it is. Go on.
So when we're using this formula, we can only use it when x equals a.
Yep, this formula, the one right at the top of the board there, gives you specifically the nth derivatives at some number a. And you only are able to find this if you know the Taylor series at that point. You don't get something for nothing. It's very limited. But as I've said, the Taylor series encapsulates all the information about the derivatives at that point only. It doesn't tell you what's going on elsewhere in the function. So, it's a funny thing, but you could have a function, you could have two functions with the same Taylor series that look like this, but then, like about this point A. But then somehow one function could go off like that, and the other function could go off like this, and the Taylor series would only converge to the function there, but the derivatives, we'd only be able to learn about the derivatives right near there. And this is why we can't tell anything about the derivatives outside there. So you don't get anything for free, I'm afraid. It's a very limited piece of information that you get out of this. But it's a good question. I mean, unfortunately, it's very limited. There was one question in a Math 104 final about 10 years ago, I think, or 9 years ago now, where they had a series like this one, and they asked for the derivatives at 2, or some other point, which was a mistake, because it was basically impossible, or a horrible computation. So that was a mistake. Basically, most problems, I suspect, you would find that you take the derivatives at 0, but there's an example where it should be at 6, because the series is in terms of x minus 6. Any other questions? I've got one more other little topic about power series. It's a big topic, and we've reduced it to one type of example. that's left, which hopefully I can cover quickly, as I said. I'm not going to have much time for complex numbers, that's for sure. That's okay. We've only got 2 more topics after this, complex numbers and differential equations. And for some reason, they've allowed 2 weeks for differential equations, but I can do it in 1. So I'm not worried. All right. Moving on to 26.4. Using Maclaurin series to find limits. Okay. The best thing for me to do is to give you one example here and use this as an illustration. Suppose you want to find the limit as x goes to 0 of e to the minus x squared plus x squared cosine x minus 1 all over 1 minus cosine 2x cubed. Okay, this is definitely a step up in difficulty from the limits that we've looked at in the past. Now, if you plug in x equals 0, which you should definitely do as a matter of course, you get 1 plus 0 minus 1. So we'll have 0 on the top, and on the bottom you have 1 minus cosine 0, which is 1 minus 1, which is 0. So you get 0 over 0. So you should use L'Hopital's rule, right? Well, you can. It's just a real pain to differentiate. You're going to have to probably differentiate the top and the bottom 6 times, I think, something like that. So that seems like a silly thing to do. So the trick is to replace everything in sight by its Maclaurin series. How do you know how many terms to use? Well, you've got to use enough terms so that you don't get 0 on either the numerator or the denominator. So that is a fine art. I am going to use terms up to, say, 6. Actually, let's do terms up to 8. What the hey? What the hey? You'll see that you don't need as many, but e to the minus x squared is going to be 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8 over 4 factorial, and so on. So that's the e to the x term. Plus x squared cosine x is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. And then somehow I have to squeeze in a minus 1 on the numerator. So that's the numerator. Unfortunately, I didn't quite squeeze in the minus 1, but what are you going to do? All right. On the denominator, I'll have 1 minus cosine 2x cubed. I guess it's worth taking a little extra little part. Look, cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. So cosine of 2x cubed is 1 minus 2x cubed all squared over 2 factorial plus 2x cubed to the 4th over 4 factorial, and so on. So actually I get 1 minus 4x to the 6th over 2 factorial. Actually, I don't even need any more terms because the next term is x to the 12th, and I've decided only to go up to 8 on top and bottom. So I have 1 minus 4x to the 6th over 2 factorial plus ... And I might as well just note, I've gone up to 8th order. That's just my personal choice. As I said, if I only go up to, if the order is too small and everything cancels out so I just get 0, then I haven't done enough. I have to do enough to get up to that. In any case, what do I get? Well, if I multiply some stuff out, let's just write it out. 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6 plus x to the 8 over 24 plus x squared minus x to the 4th over 2 plus x to the 6th over 24 minus x to the 8th over 1 over 720 minus 1. Notice that when I multiply the x squared by the x to the 8th, I actually get x to the 10. So I'm not even going to bother writing it. It's going to be absorbed in the dot, dot, dot at the end. So these are all the terms up to x to the 8th. On the bottom, well, I have the same thing. 1 minus 1 plus 4x to the 6th over 2 factorial, and so on. So this, again, is all the terms up to and including x to the 8th. The 1 goes away. The x squared goes away. The x to the 4th over 2 goes away. But the rest of it won't go away. So I've got on the top x to the 6th over 24 minus x to the 6th over 6, which is minus x to the 6th over 8. And kind of have to sort of do this 1/24 minus 1/720, although it's not going to matter. This is the x to the 8th term here, 1/24 over minus 1/720. I think this is 29 over 720, because 24 into 72 is 3, and so it's 30 minus 1. But this is supremely irrelevant, rather. 29 over 720, x to the 8th, and so on. The denominator is 4x to the 6th over 2, and so on. All right. That is accurate up to 8th order. Everything in the dot, dot, dots is x to the 9 or greater. So now divide top and bottom by the highest power, rather the lowest power around, which is x to the 6th. And you're going to get minus an 8th plus some irrelevant number times x squared plus dot, dot, dot. And now everything is higher than x squared in this. And on the bottom, I just get 2, because 4 over 2 is 2, plus higher order terms. Again, everything here is x cubed and higher. And everything here is x cubed and higher, right? In the original up here, before we divided, the dot, dot, dots included everything that's x to the 9th and higher. So when we take away 6 powers, we have x cubed and higher. Now, when x goes to 0, all of the higher order stuff goes away, and you get minus a 16th, or minus 1/8 over 2, which is minus a 16th. And that's the answer. Right, so the technique, write out the Maclaurin series for everything in sight, use enough terms so that if you cancel, then you don't just get a 0. If we'd only gone up to 5th order or 4th order or something, then the top and bottom would both be 0. You can tell this because in the canceled series over here, after you've canceled everything out, there are no 4th order or lower, or even 5th order. It starts at 6. So it becomes like a poly over a poly, but it's like an infinite poly. You just need to find the lowest degree term on the top after canceling, and on the bottom after, multiplying and canceling, and then the ratio. All right? These things are fairly straightforward. Another example, which I'm not even going to finish, I'll leave it to you, is if you had something like limit 1 over x minus 1 over sine x. Now that's too simple. 1 over sine x minus 1 over e to the x minus 1. This is not actually a fraction as it stands. They're both infinite in the limit. But the way you prepare it is to take a common denominator, sine x times e to the x minus 1. And on the top, you're going to have e to the x minus 1 minus sine x. And it's pretty similar to the other problem. You should work that out for practice. And I think the answer turns out to be a half. So that's an exercise for you. And it's in 26.4. All right. Hopefully I have about 10 minutes to at least introduce the idea of complex numbers so that I can finish the topic next time. Are there any other questions about that last little topic there, finding limits? Obviously you've got to practice it, but I don't have any questions about it. I should say, by the way, that actually the Maclaurin series don't even have to converge for that to make sense. Not that it really makes a difference in any of these examples. But even if it doesn't converge, you can still just use a Maclaurin polynomial. You don't really need the full series. Chop it off somewhere. All right. So, do I in fact have 10 minutes? I do. Very good. All right. Let me give you the very brief introduction to complex numbers, just the basic arithmetic properties of complex numbers. So, I'd like to take a square root of minus 1 because this old thing has two roots, 1 and minus 1, whereas this has no roots. But let's even the score, and let's say that I squared equals negative 1. I stands for imaginary. So I squared is negative 1, and therefore I squared plus 1 is 0. And all of a sudden we found a root. Of course, the other root is minus I, because minus I squared is minus 1 squared times I squared, which is 1 times minus I, 1 times minus 1, which is minus 1. So minus I is the other root of this equation. So this actually factors into x minus I, x plus I, where I doesn't really exist because it's imaginary. All right, so having defined this I very quickly, we can find square roots of other negative numbers, such as minus 4. Well, 2I squared is 2 squared times I squared, which is 4 times minus 1, which is negative 4. So the square root of negative 4 is 2I. And of course, the other square root is minus 2I. So every number now has two square roots. Even 0 has two square roots. They are the same, however, 0 and 0. Multiplicity 2, we call it. But the fact is that negative numbers now have square roots. You can add real numbers and so-called imaginary numbers. 2I is an imaginary number. But a number like 3 plus 2I is a real number plus an imaginary number. You cannot simplify that down anymore. This is called a complex number. Bless you. So a complex number looks like x plus either iy or yi, depending on how your mood is. Doesn't matter. Where x and y are real numbers. They could be 0, they could be negative, they could be irrational. They're just any real numbers. And together, the collection of all the complex numbers is denoted by C for complex. So it's like a bold C. All right. So 2I is a complex number by itself, by the way. You can think of that as 0 plus 2I. So that's complex. Imaginary numbers are complex. Real numbers are complex too. 3 is 3 plus 0I. So C includes R embedded in it. It's an extension of R. X plus IYI or IY, the real part, so if Z, we normally write these things as Z. So if Z is x plus IY, the real part of Z is x. And the imaginary part of Z is y. So specifically, the real part of 2 plus 3I is 2. And the imaginary part of 2 plus 3I is 3. Not 3I, actually. The imaginary part, by definition, is just the real number out the front of the I. What is the imaginary part of 5 minus 7I? It's negative 7. How about the imaginary part of 3I? Well, it's 3. What's the real part of 3I? Well, it's 0. There's no real part. Okay, so this gives you the idea. Real numbers have imaginary part equal to 0. Okay, well, that's all not very exciting. You can add and subtract complex numbers in a fairly obvious way. Here's an example. 2 minus 3i plus minus 6 minus 7i. These are two complex numbers that I want to add together. I just add the real parts. 2 minus 6 is minus 4. And then I add the imaginary parts. Minus 3 minus 7 outside of I is 10i. The same thing for subtraction. There's not too much to it. If you're going to multiply these things together, it's a little more interesting. You just have to expand as normal. You get minus 12 plus 18i minus 14i plus 21i squared. But of course, the key is to realize that I squared is negative 1. So altogether, you get minus 21 and minus 12. So you're going to get minus 33 plus 4i. And that, I hope, agrees with what I had. Now, what should I cubed be? We know what I squared is. What is I cubed? Well, it's I squared times I. And I squared is negative 1. So I cubed is the same as minus I. How about I to the fourth? Well, that's I cubed times I, which is minus I times I, which is minus I times I is minus 1. So you get 1. So I to the fourth is 1. So what's I to the fifth? Well, that's I. I to the sixth, negative 1. I to the seventh, negative I. I to the eighth, 1. They are periodic of period 4. Every fourth power of I is 1. And so all the powers just cycle through 1i minus 1 minus I, and so on. So I to the 100, for example, is also 1, because 100 is a multiple of 4. Whereas I to the 101 is I, because 101 leaves remainder 1. So you can always knock out fourth powers. The only other thing I really have time for tonight, in the last 5 minutes, is division. I want to show you how to divide complex numbers because it is not quite trivial. And I fit it on this bottom board. Here goes. In order to motivate the division, I want to point out some nice facts. Suppose you have a complex number x plus iy, and you multiply by x minus iy. What do you get? Well, you have a difference of squares, right? This is going to be x squared minus iy all squared. But I squared there, when you pull it out, is negative 1. So actually, you get x squared plus y squared. Not x squared minus y squared. That's the difference between a normal conjugate and this so-called complex conjugate. When you multiply them together, you get a nice x squared plus y squared. It's not only a real number, it has to be positive, because squares are positive unless x and y both happen to be 0. So in summary, suppose I start with z equals x plus iy. The conjugate expression, which is called the complex conjugate, or just conjugate, is z bar. It's written like z with a bar over it, and it's x minus iy. And what I'm trying to tell you is that z times z bar is equal to x squared plus y squared. Now this quantity x squared plus y squared is pretty useful. In fact, I'm going to define the absolute value of z to be equal to the square root of x squared plus y squared. That's sort of Pythagoras' theorem motivation. We'll look at that next time when we look at the complex plane. This is true if z equals x plus iy, of course. This is the absolute value. By the way, if z is a real number, you get the square root of x squared, which is just the regular absolute value. So this is the general complex version of the absolute value, which for some reason is not called the absolute value, but is called the modulus of z. But it's compatible with the absolute value. Anyway, the point is this is the square of the modulus. So in other words, z times z bar is the absolute value or the modulus of z squared. So what's the point? The point is that you've got this nice conjugation sort of rule. So, for example, maybe I should have given myself a little more board space. Never mind, I'll make it work. 2 minus 3i divided by minus 6 minus 7i. Say I want to find that. Well, what I do is I multiply top and bottom by the conjugate. It's a very familiar trick, but the difference is we're dealing with complex numbers here. So instead of a difference of squares, it's really a sum of squares. The conjugate expression of the denominator is negative 6 plus 7i. So I switch the imaginary part around from, in this case, minus to plus. And on the bottom, I do the same thing. So to divide complex numbers, whoop, there goes the plant. To divide complex numbers, I have to multiply top and bottom by the conjugate. Let's look at the bottom first. The bottom is quite simple. I don't compute it. I just know what it is. I know it's minus 6 all squared plus minus 7 all squared. It doesn't matter if you leave out the minus, because we're going to square it anyway. So it's just 6 squared plus 7 squared. Beautiful. You don't need to do anything. Unfortunately, to do the top, you need to do this multiplication again. And so we better multiply it. 2 minus 6 is a minus 12. I get plus 18i. I get plus 14i minus 21i squared. All right. So let's finish it. What's I squared? Negative 1. So actually, this will give me a plus here, and I'll get 21 minus 12 is 9. So I get 9 plus 32i all over 6 squared is 36, 7 squared is 49. I add them up. 49 plus 6 is 55, plus 30 is 85. I get 9 plus 32i over 85. It doesn't quite look like it's x plus iy, but of course you can split it up into 9 85ths plus 32 85ths I. And now it is in x plus iy form, or yi. So the only thing I want to comment, and I'll just move up here to do it, is that if the problem was to find the imaginary part of this ratio 2 minus 3i over minus 6 minus 7i, you would have to actually do everything we just did on the bottom line and work it out, and you get 9 85ths plus 32 85ths I, and you can just read out the imaginary part is 32 85ths. Of course, you could also read off the real part as 9/5 too. All right, well, are there any questions about that for the time being? I think that is what I have time for today. So next time, no questions? All right, next time we'll get into the meat of complex numbers.